Hello everyone, let's analyze. So we're going to start off today with the definition of a subsequence. Right? So what's a subsequence? Well, given a sequence of numbers, a subsequence is essentially an infinite sampling of the sequence where the sequential ordering is kept. More precisely, if n of k is a mapping of natural numbers to natural numbers, and n of 1 is less than n of 2 is less than n of 3, then we can build a subsequence of the sequence an by only extracting the entries n of k, right? So a n of 1, a n of 2, a n of 3, so forth and so on. So just to give a couple of examples of what we mean by a subsequence, we can think of the sequence of natural numbers written in order: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so forth and so on. And we could take a subsequence of the prime numbers written in order: 2, 3, 5, 7, 11, 13, 17, and so forth. Right? We can see that in red in the original sequence, right? The red entries are the prime numbers. That's where I'm sampling, right? So I'm sampling these prime numbers. Okay, I'm extracting in order certain entries from my sequence. Another example, given a generic sequence, A1, A2, A3, A4, A5, A6, I can extract every even entry: A2, A4, A6, A8, A10, A12, and so forth. Right, so I'm extracting all the even entries of the original sequence. Right? In other words, I'm building another sequence, right, by taking every 2k entry, right? We see here that my index is a function of k as k goes from 1 to infinity. Okay. So note that the way we pick the indices to keep or to sample in a subsequence, right, we have to keep them in order. In other words, the first index taken, n of 1, is less than the second index taken, n of 2, is less than the third index taken, n of 3, and so forth, right? So that itself is a sequence of natural numbers that is, well, as you can see, increasing and necessarily unbounded, right? So can you explain why that is? I think you can. Can you explain why, for example, the kth index taken, n of k, is at least k? Okay, so now we have the vocabulary for our next result. A sequence converges if and only if every subsequence converges. In other words, every which way you can sample the sequence. If every which way you can sample the sequence to build a subsequence, you get convergence, then the entire sequence converges. So let's prove this statement. As of course you all know, since this statement is an if and only if statement, we have to really prove two things. That convergence of the entire sequence implies convergence of every subsequence, and that convergence of every subsequence implies convergence of the entire sequence. So suppose the entire sequence converges to a limit a, right? That's what we're assuming, right? So we say we know this. Well, we know this, so let's write what does that mean? What's the definition of such a thing? An converges to a limit a. Well, let epsilon be an arbitrary positive number. We know there must be some natural number n for which the following statement is true. if little n is greater than or equal to big N, then the difference between AN and A is smaller than epsilon. So that's true. Okay, now let's consider a subsequence. Which subsequence? Any subsequence, an arbitrary subsequence. In other words, I'm going to build a subsequence, right, by finding some arbitrary sampling n of k. Okay. Now, remember, little n of big N is at least big N. Now let's think. When would the big N sample be equal to big N? Well, that's if my sampling is just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way through big N. In other words, my subsequence includes all of the sequence entries up to big N. But if it doesn't, then of course n of n is bigger than big N. Right? Remember, each of these numbers are positive integers. And before this one, there are n minus 1 ordered positive integers. So, if k is greater than big N, then n of k is greater than big N. So that means I could take the convergence statement here and know that if k is bigger than big N, then n of k is bigger than big N, which means a n of k minus a in absolute value is less than epsilon. This means that the subsequence a n of k satisfies the definition of convergence. And it was an arbitrary subsequence. So we've proven that if the entire sequence converges, then every subsequence also converges. Furthermore, we also show that every subsequence converges to the exact same limit. Suppose now, to prove the other implication, that every subsequence of the sequence converges. Well, one way to sample a sequence is to just take every single entry. In other words, every sequence is in fact a subsequence of itself. And that subsequence converges because we assume that they all do. So if every subsequence converges, then the entire sequence must converge because it itself is a subsequence. So that direction was much simpler. Okay, now that we've stocked our analytical toolbox with various types of goodies, we can now address this wonderfully strange object below. That is, what is the square root of 2 plus the square root of 2 plus the square root of 2 plus the square root of 2 plus, and it keeps going. Forever, in fact. I mean, what is it? Is it anything? Is it a number? A bird? A plane? A unicorn? Infinity? Or perhaps beyond? Well, hidden inside the ellipsis here lies implicitly the idea of a limit. So, since there's an implicit limit, and I could cut off this sequence of square roots at various moments, I can actually represent this as a sequence. And, well, we've got all kinds of tools for analyzing limits of sequences. So, get your tools ready, steady yourself, and let's seek what this hidden limit is. So, first we're going to recast this object here as a sequence. Let the first number in the sequence be the square root of 2. The second number is the square root of 2 plus the previous number, and so forth and so on. The n plus first entry is the square root of 2 plus the previous entry. Now, in order to build up a little bit of intuition about what this sequence might look like, I've taken the liberty of plotting the first 20 entries. So, of course, for n equals 1, we have the square root of 2. And for n equals 2, we have the square root of 2 plus the square root of 2 here. And, well, if we observe this plot, it appears that my sequence converges to 2. It also appears that my sequence is increasing. So, let's use that to formulate a plan. From this picture, I'm going to make a claim. The sequence converges to 2. That's my claim. Now, note, this picture is not a proof. Right? We don't know what happens in the 21st entry, or the 30th entry, or the 172nd entry, or the Googleplexith entry. So, in spite of the picture, and however compelling it may be, we still have to prove the claim. So let's prove it. Now, I know that a bounded monotone sequence converges. I know that that's true. In fact, you proved it in class just last class. So if I can show that this is monotonic, which it appears to be, and bounded, which it appears to be, above by 2 and below by, well, the square root of 2. So if we can show that it's bounded and monotonic, then we have proven, using the result from last class, that a limit L exists. Now, to be clear, that would not be sufficient to prove that L is 2. For that, we'd have to show explicitly that L satisfies the definition of a limit, that 2 satisfies the definition of the limit, and furthermore, or we could prove that 2 is the least upper bound of all upper bounds. So, again, I claim the sequence is monotonically increasing and bounded above by 2. Okay, well, it's clear that the first entry, which is the square root of 2, is less than 2. So, I've proven that the first entry is bounded by 2. Now just infinity minus 1 to go. That's an analysis joke, by the way. Infinity minus 1 is infinity. Now, let's show that the first 2 entries are increasing. In other words, let's show that A2 is greater than A1. Well, A1 is the square root of 2, and that's positive. We know that. And we can add 2 to both sides of this inequality to obtain this. 2 plus the square root of 2 is greater than 2. And because the square root is an increasing function, we showed that earlier in the semester, I know that the square root of 2 plus the square root of 2 is greater than the square root of 2. On the right, I have A1. On the left, I have A2. A2 is greater than A1. Okay. So again, I've made the claim that the sequence is bounded above by 2 and that the sequence is monotonically increasing. And I've showed that the statement is true for the first entry. The first entry is bounded above by 2, and the first entry is less than the second entry. To show that this is true for all entries, we're going to use the logical tool of induction. In other words, we're going to show that if it's true at the nth entry, then it must be true at the next entry. And since it's true at the first, that means it'll be true at the second. And if it's true at the second, it'll be true on the third. And if it's true in the third, it'll be true on the fourth, so forth and on forever and ever and ever, and that would be a proof by induction. So suppose that the nth entry is bounded above by 2. Well, then I can add 2 to both sides and maintain inequality. I can take a square root of both sides and maintain inequality. On the right, I have the square root of 4, or 2. On the left, I have an plus 1. So an plus 1 is less than 2. All right. So if the nth entry is less than 2, then the next entry is less than 2. And since I know already that the first is less than 2, I now know that every single entry is bounded above by 2. Now, let's assume that an plus 1 is greater than an. Right? In other words, we're going to suppose that I have increasing at a single nth and n plus first term. Well, I'm going to follow the same trick as before. I can add 2 to both sides and maintain inequality. I can take the square root of both sides and maintain inequality. And I have on the left an plus 2 and an plus 1. So if an plus 1 is greater than an, that implies an plus 2 is greater than an plus 1. So since we know already that a2 is greater than a1, we know that a3 is greater than a2, and a4 is greater than a3, and a5 is greater than a4, and so on forever and ever and ever, ever. So we've proven that the sequence is monotonically increasing, strictly monotonically increasing in fact, and bounded above by 2. So limit L exists, right? It's monotonic, it's bounded, a limit must exist. Now again, we haven't yet proven that the limit is 2, right? Because so far as we know, 2 is an upper bound. We don't know that it's a least upper bound. Even though the picture suggests that it likely is, we haven't proven it. So allow me to give a quick sketch of the remainder of the proof, right? The idea in this sketch is exactly the idea behind the remainder of the proof, but it's important that when we do the proof, we do it rigorously, where every step is valid. But again, the idea remains the same, and we want to think about how can we think about such objects as the square root of 2 plus the square root of 2 plus the square root of 2, so forth and so on. Okay? We essentially have said that this sequence, because of the infinite character suggested by the ... that what this represents really is the limit of a sequence. All right, it represents the limit of a sequence where each sequence entry is a partial square root of square roots. And we said that that limit is L, right? Well, if I notice inside the radical, I have the square root of 2 plus, well, this is actually equal to the entire thing, right? In some sense, it's kind of a self-repeating pattern, right? After the first plus, I have the square root of 2 plus the square root of 2 plus the square root of 2 forever and ever and ever. Remember, infinity minus 1 is still infinity. If I remove one term, I still have an infinity of terms. So if in fact this object is equal to L, L is equal to the square root of 2 plus L. I can square both sides, and I get that L squared equals 2 plus L. I have a quadratic equation, which has, at most, 2 solutions, and this has 2 solutions. Specifically, L equals -1 and L equals 2. Now, L cannot be -1. Why is it? Well, we proved that a monotonically increasing function that is bounded must converge to the least upper bound. -1 is not the least upper bound. In fact, it's not an upper bound at all, right? The very first entry of my sequence is greater than -1. So -1 is not the limit. But the limit does have to satisfy this equation. Sorry, this one here. L squared equals 2 plus L. So that means L can only be 2. Okay. All right, now let's demonstrate the same idea as the sketch rigorously using the tools in our toolbox. Since L is equal to the limit of the sequence, and every subsequence converges to L, we learned that, well, just a few minutes ago, in fact, then L is equal to the limit of a k plus 1 as k goes from 1 to infinity. That's the subsequence where I basically just knock off the first entry, right? It's A2, A3, A4, A5, and so forth. Well, ak plus 1, by the definition of the recursion, is the square root of 2 plus ak. And notice I have a limit of the square root of a sequence. And we showed in a previous in-class assignment that that's equal to the square root of the limit of 2 plus my sequence. We also know that limits of sequences that converge can be added together. And 2 is the limit of the sequence 2, 2, 2, 2, 2, 2 forever, the constant sequence. Right? And of course, ak from k equals 1 has a limit. Specifically, the limit is L. So this is 2 and this is L. So I have L equals the square root of 2 plus L. As before, I can square both sides. I have a quadratic equation. How do we solve quadratic equations? Well, typically we move every non-zero term to one side of the equality and factor if possible. And if not possible, there's a quadratic equation available for our use. But this quadratic equation happens to be nicely factorizable. So L is 2 or -1. We know already why L is not -1, so L must be 2. And now we have unmasked the limit hidden inside these ... dots. We know what this object is. It's 2, the number 2 in disguise. But the number 2 didn't get away with it. It would have if not for this pesky real analysis tools. And that's it for today, folks.